Welcome everyone to section number 3. This is double integrals over general regions. The claim is hopefully by now we're pretty good at integrating over rectangles, but what if we want to do something more, something beyond rectangles? So in this lesson, right, our goal is we're going to learn how to integrate over general, right, non-rectangular regions, and eventually we're going to get to how to switch the order of integration and see eventually why this is necessary. So we're going to learn the basics though in this video, and in class we'll do a lot more. All right, so to kind of help motivate this or to get us moving in the right direction, I want to go over a couple examples here. So I'd like to find the volume under this function here, a boring function. F of xy is equal to the nice constant value 3. And I'm going to start with a rectangular region, right? So I'm going to have the rectangular region bounded by these lines right here. So let's go ahead and sketch out our region R. So the region R, let's see, the first one is x equals 0. So that's going to be a nice vertical line here, x equals 0. The next one, x equals 4. So 1, 2, 3, 4. Again, a nice vertical line here. Y equals 1. There we are, a nice horizontal line. And then y equals 6. 2, 3, 4, 5, 6. Something like this. And the region that's bounded between these curves is going to be this inside one right here. This is going to be our R. So this is the region that we would be integrating over normally. Okay, so in this case we have the function 3, and I would like to know what is the volume trapped under this function, the surface really, over this region. Okay, well, since it's a nice constant function here, we know that it's going to be basically a rectangular prism. And if you want volume of a rectangular prism, well, we know a beautiful volume equation, right? It's just length times width times height. So if I say this is my length, this is my width, and my height is 3, right? This surface is hovering 3 above, right? Well, we can calculate this out. So volume, let's see, length, this is going to be 5 in total, right? Basically, this is just 6 minus 1, so that's 5, times the width, that's going to be 4, right? 4 minus 0, again, if you count this up, this is 4. And then the height is 3. So, okay, 20 times 3, that's going to be 60 altogether. So I would suspect that the volume, right, so if I evaluated some double integral, right, we would get out 60. So let's go ahead and confirm that, right? And the claim is we know how to switch the order of integration. It's Fubini's theorem. You can integrate in kind of either order. It's very nice. So I'm going to go ahead and I'm going to evaluate out this first one, and I'll leave the second one for you here. Okay, so again, our y's are going from 1 to 6, our x's are going from 0 to 4. So that's how this was set up. So let's do an integral with respect to y first, right? So if I integrate with respect to y, that's going to be from 1 to 6, and this is just a constant, right? So this is going to become 3y. Now I need to evaluate from 1 to 6, and I'm leaving my dx, my x integration for just a second. So okay, if I plug in 6, right? So 3 times 6 would be 18. Minus, if I plugged in 1, that would be 3 times 1, 3. So actually, let me go ahead and simplify this. 18 minus 3, let me just write 15. And now I need to still integrate with respect to x. Well, if I integrate with respect to x, I'm going to have 15x. Again, I need to evaluate that from 0 to 4. Well, if I plug in 4, I'm going to get out 60. And if I plug in 0, I'm going to get out 0. So this is just going to be 60, which is great, right? This is exactly what I suspected the answer would be, right? I thought that I would get out 60. Okay, so this was a rectangular region. This is something that we've dealt with before. Now it's time to upgrade. Now I'd like to do things over a triangular region and show you how this kind of changes. Okay, so again, let me go ahead and sketch our region R that we want to integrate over. In this case, we're switching it up. We still have x equals 0. So it's going to be this line right here, and we have y equals 6. 1, 2, 3, 4, 5, 6. So something like this. But now we have this line. So y equals 5/4 x plus 1. So let's go ahead and try to sketch this straight line. I'm going to do it with a couple of points here. So for instance, if I plugged in 0 for x, 0 for x, I would get out 1 for y. So I know that this point right here is on this line. Another maybe nice point to plug in would be x equals 4. So right, if I did 1, 2, 3, 4, if I plugged in x equals 4, that perfectly cancels with that fraction there, right? So 4/4. So that just gives me 5 plus 1, that's going to be 6, which happens to be perfectly on this line right here. How nice. All right, so our line is going to be a nice straight line connecting these 2 points. So there is my triangular region now. something like this. This is my new region R. There we go. And actually, if you compare these two, the claim is I chose these things very particularly because it's just this one cut in half. So something like that. Or if you'd like to, right, you could kind of extend this, and you would see that, again, it's just that one cut in half. So there we go. So if we had to guess, what is the volume, right? Again, still under this curve, this surface, f of xy equals 3 over this region, well, you would suspect that it would be half as much as it was originally, right? You would suspect 30. Or you can even use, right, we know an area of a triangle, 1/2 base times height. So you would do 1/2 base times height, and then, well, so that's just for the triangle, and then we multiply by 3, because again, the surface is hovering kind of 3 units above the xy plane. So times 3, and if you evaluated this all out, again, it looks very similar to this over here, it's just now you have that half, you would get 30. Alright, so our sneaking suspicion is that if we integrated something, we would get out 30. And so the question becomes really, what should we integrate? So now I'd like to go ahead and teach you how I think about these, kind of setting up these more complicated double integrals. So in this case, let's go ahead and try to set up an integral here, and I'm going to integrate with respect to y first, and then with respect to x, and then we'll do the other one here in just a second. Well, the function that I'm integrating is the same as before. It's just the function 3, right? So f of xy equals 3. So that's not the complicated thing. It's really setting up the region, right? What are our bounds of integration? So the way that I think about this is for the y, I imagine that I'm trying to integrate over this region. I'm kind of moving in this y direction. I'm moving up in this y direction, right? And I wonder, what is the first line that I run into? And well, before, if I think about this, the first line that I ran into was y equals 1. And kind of it's not a coincidence that you had a 1 here. And then you exited out of the line y equals 6. So kind of, again, we're kind of moving up, and you say, when do I need to start counting up my volume? And when can I stop counting up my volume? That gives us the upper bound there. So in this case, when I'm moving up, you can see, well, I need to start at different heights, right? That it really depends on where I am in the x, right? So in this case, well, it's instilled in this equation here, y equals 5/4 x plus 1. So I need to start adding up this volume as soon as I run into that line. And luckily, this is a y value, right? So when I'm integrating with respect to y, I'd like to have y bounds. So I'm going to go ahead and put 5/4 x plus 1. So that's going to be my lower limit of integration. And then as I continue to move up, right, I run into y equals 6. So I'm going to go ahead and try 6 as my upper bound of integration. Again, this is just kind of guessing a little bit right now, and then we're going to check, and hopefully when we integrate it, we get out 30. Now, after we go ahead, we've already kind of instilled this fact that, right, we run in at different points here, different heights, right, along this line. So we already got that. So now I think about, okay, if I'm just interested in x values, when do I start integrating? When do I stop integrating? Well, in this case, I'm going to do from 0. That's when I run into this region first, kind of as I'm moving left to right. I do 0, and then I stop at 4. Stop at 4 there. So that's how I'm going to do the setup. Let's go ahead and see if this is correct. So again, we're going to integrate with respect to y. Well, if you integrate 3 with respect to y, you get 3y. And now I need to evaluate it at 6 and at 5/4 x plus 1. Okay. Well, if I plugged in 6, I would get out 18 again. And then I need to subtract away when I plug in 5/4 x plus 1. So this is going to be 3 times 5/4 x plus 1. And I still need to integrate with respect to x here. Let's go ahead and take one line and simplify this down a little bit. So integrating from 0 to 4, I'm going to have 18, and once I distribute this -3, right, I'm going to be subtracting by 3. So that's going to be 15. And then I need to subtract away, right, so -3 times 5/4 x, that's going to be -15/4 x dx. There we are. Okay, well, let's go ahead and now integrate that with respect to x. So I'm going to have 15x minus 15/8 x squared, evaluated from 0 to 4. Again, we can check our work, right? If I take the derivative of this, I should get back to where I started. Okay, now let's plug in 0 and 4. Well, when you plug in 0, right, that's just 0. That's very nice. When I plug in 4, okay, oops, sorry, I forgot this is 15. Huh. Okay, now, when I plug in 4, I'm going to get 15 times 4, that's 60, minus, that's going to be 15 eighths, and 4 squared is going to be 16. We get a little bit of nice cancellation here, so 16 and 8, that just becomes 2. And so we're going to get 60 minus 30. 60 minus 30 is, ta-da, 30, right? So we got the answer that we suspected there. Okay, so that's if I wanted to integrate with respect to y first. Now I would like to go ahead and set up the integral, right, if I wanted to integrate with respect to x first. So again, I'm going to be integrating over the same function, 3, but now I'm going to do dx first and then dy. So in this case, I imagine, since I'm integrating with respect to x, I imagine that I'm moving in this x direction, right? So I'm moving in the x direction, I'm moving from left to right, small x values to large x values. Just like before, I was moving in the y direction, so I was doing small y values to big y values, and I was moving kind of vertically. Now I'm moving horizontally. And the first time that I run into a line that kind of, we have the region here, is this nice vertical line. It's just x equals 0. So that's when I'm going to start integrating, is at x equals 0. Again, you can see that x equals 0 kind of shows up over here. But now as I exit the region, right, I exit through this line right here. But I need x equals something, right? This needs to be an x value. I have y equals, but I need it to be an x value. So I need to solve this for x. And when I do this, right, I'm going to get y minus 1 is equal to 5/4 x. And so I can get x is equal to 4/5 y minus 4/5. And now this is an x value. It's x equals, right? And it still tells you about this line right here. So again, when you're integrating with respect to x, right, with this little dx right here, you need x values. Just like when you're integrating with respect to y, you need y values. So this is y equals, right? So it's a y value, 5/4 x plus 1. Okay, so now we exit through, again, this line right here, but it has 4/5 y minus 4/5. So 4/5 y minus 4/5. Okay, kind of crowding my 3 a little bit, but that's okay. Let's go ahead and move it over a little bit. All right, now that we've taken care of this, and we've already kind of told it about that we have these complicated lines, now we think about, okay, if I'm moving in the y direction, well, I run into this region first at y equals 1, and I exit through y equals 6. Y equals 1 and y equals 6. It's important here that these last values, right, they're constants. I know it's kind of tempting. Well, you could say that the y values, again, you could talk about this line right here. But if you integrate that, the last thing, these y's, and you had something more than just constants, right, you wouldn't get out a number. And that's a problem, right, because you want this to be a number. It's got to be a volume, right? And so your volumes, it shouldn't have any x's or y's in it. It should just be a number. Hopefully it's the number 30. Okay, so this is the setup right here. I recommend pausing the video, trying this one out on your own, and then I'm going to go ahead and spoil the surprise. Okay, so pause the video, try it. All right, and there's my work. So again, I integrate with respect to x first. So I get 3x, I go ahead and I plug in, everywhere I see an x, I plug in the 4/5 y minus 4/5, and then I plug in 0, which gives us 0. Now I integrate with respect to y. I get this, and I plug in 1 and 6, and it takes a little bit, but indeed we do get 155ths, aka 30. So either way, we get the same result, and it's the result that we expected, 30. Okay, so in general now that we kind of have this idea about moving maybe in the y direction or in the x direction, stuff like this, now let me go ahead and give you the theorem. So this is an upgrade of Fubini's theorem. This is the stronger form of Fubini's theorem. And in this we have kind of two cases. The book kind of defines these two types of kind of regions that we have out there. So this region D, we're calling this D, if it's defined by these xy values such that x ranges between a and b, and y ranges between two functions. So they're functions of x, so g1 of x and g2 of x. Then the claim is the double integral. Remember, this is calculating maybe out volume under this function, f of xy. Well, this is going to be equal to the integral from a to b and the integral from g1x, g2x of our function f of x, y, and then we integrate with respect to y first, and then with respect to x. Okay, the book defines these as type 1 regions. Type 1 regions here. So I'm not going to be so specific, at least when it comes to quizzes, and I think typically on exams and stuff, they haven't ever referenced type 1 or type 2 regions, but this is what it is. And let me go ahead and draw a picture for us here. So let's go ahead and maybe here is our A and here is our B. We have two functions with respect to x. So let's see, here's maybe our first function, and here's maybe our second function. So something like this. Both of these, again, they're passing the vertical line test. They're functions with respect to x. And so maybe you have something like this. Again, we only really care between A and between B. And so our region R is going to be this one right here. Maybe I'll go ahead and use purple, a bit smaller one here. And so this is what our region looks like. Something like this. So this is a type 1 region. Okay, the other kind of region that we can counter is one where you should integrate with respect to x first. So in this case, maybe x is a function of h's, right? H of y. So h1 of y, h2 of y, and then y ranges between c and d, some constants here. So again, this is going to be a type 2 region. I think they even use these Roman numerals here. So type 2 region. In that case, the volume under this function, or the surface, right, is going to be equal to, and then I would go ahead and integrate with respect to x first. So it's going to be with respect to x, it's going to be h1 of y, h2 of y. Again, we're integrating the function f of xy. Let me go ahead and move over this dx a little bit. And then we integrate with respect to y. And y goes from the constant c to the constant d. And again, let me go ahead and sketch so I can show you what these type 2 regions they look like. So in this case, y goes from the constant c to the constant d. And if we have x as a function of y's, right, then this means it's actually passing the horizontal line test. So it looks something like this. That might be our h1. And then our h2 might be something like this, h2. I guess I really should have labeled these things. I kind of forgot back here. So this is maybe g2, and this is maybe g1. Okay? And so let's go ahead and kind of sketch off where this gets cut off in the top and in the bottom, something like that. And so here is our region R. And again, let me go ahead and shade it for us. Okay, so these are type 2 regions. There's ones where you should really integrate with respect to x first and then with respect to y. Okay, a big remark here, something that I want you to pay attention to, is that the final integral, right? Notice that this final integral here in both of these cases, right, always has just numbers, right? So the final integral should always just have numbers, is what I'll say. Just have numbers. No variables. If you have variables, your answer will not be a number, and that's a problem, right? Because it's supposed to be volume, right? And so again, you really cannot have variables here in the last one. So again, so c to d, so these should be constants. A to b, again, constants. You can see when we did it back up here, right? Our final integral, 1 to 6, here 0 to 4, so they should just be numbers, no variables. All right, but before we go, I got one more example for us here on the next page. Sketch the region and evaluate the integral from 0 to pi over 4, 0 to secant of x, dy dx. So again, let's go ahead and sketch this region, and then we're going to go ahead and evaluate out the integral. So in this case, my x's, right, my x's are ranging from 0 to pi over 4. So 0 to pi over 4, I'm going to say, is right over here. 0 to pi over 4. And okay, so these are nice vertical lines, we think of them as. And so the functions here are y equals 0 and y equals secant of x. So y equals 0, so that's just the x-axis here, and y equals secant of x. Well, that we maybe need to remember back from our trig days, or maybe even calculus 2 or something like this. We really played a lot with these secants. So, okay, let's go ahead and review, right? So secant of 0. Secant of 0, well, that's 1 over cosine of 0. And that's going to be, well, 1 over 1, which is 1. So at 0, right, secant has height 1. Okay, well, how about at pi over 4? So if I wanted the secant value at pi over 4. All right, so secant of pi over 4, well, that's going to be 1 over cosine of pi over 4. And that's going to be 1 over root 2 over 2, which is the same thing as... I don't want to kind of go too far over there, so let me write 2 over root 2 down here. And if you were to rationalize the denominator, the cleanest way you can write this is just root 2. Okay, so, okay, a little bit higher than 1, not quite 2, but okay. Up here we have root 2. So again, this is root 2, and this is at height 1. Okay, so from this, we can go ahead and maybe guess what the curve actually looks like. And you can verify using your favorite graphing utility. So it looks something like this. And it'll actually continue in this direction. It kind of continues back up. And right, it does have some vertical asymptotes at pi over 2 and negative pi over 2. Luckily, we only care about this region right here. So again, kind of we're entering in through 0 and we're exiting through secant of x on the interval from x equals 0 to x equals pi over 4. So this right here is a picture of what our region looks like. So there's our region. Now, in this case, well, let's evaluate out the integral, right? And we'll see kind of we have this function, which just actually depends on x in this case. It's secant of x, kind of you have to imagine it as a surface kind of hovering above this region here. And then we want to know what is the volume under that surface on this region. So, okay, let's go ahead and evaluate this out. It's specifying that we need to integrate with respect to y first. So I don't see any y's here, so this is just constant with respect to y. So I'm going to go ahead and write 0 to pi over 4. When I integrate with respect to y, I'm going to get y times secant of x. And I need to plug in 0 and secant of x. I still have to integrate with respect to x here in a second. Okay, so if I plug in secant of x everywhere I see a y, I'm going to get, well, secant squared x. Right? Because secant x times secant squared. And if I plug in a 0, well, that's just going to be 0. Okay, now integrating secant squared. Secant squared, well, we should remember this. It's tangent. And now we evaluate from 0 to pi over 4. Hopefully we're getting pretty good at these. Right? Tangent of pi over 4 is 1. Tangent of 0 is 0, so our final answer is a nice, beautiful 1. So that right there, again, this is representing some volume, right, under the curve secant of x, and it's on the region from 0 to secant of x and 0 to pi over 4. Now let's go ahead and check and see what this looks like really quick. I'm going to bring up the Monroe 3D Calc Plotter. It's always good to see, right, what we're doing with these things. Right? What are we actually calculating here? So again, I went ahead and I added a region here. And so, okay, my bottom, right, in this case is 0. And, oops, sorry, this is my top. My top is secant of x. And my bottom is 0. Okay? X ranges between 0 and pi over 4. Okay? My 3D top, right, in this case is just the function secant of x, and the bottom here is still 0. Okay, so let's go ahead and sketch this really quick, and we can see, okay, this actually looks quite a lot like the region that we had in the picture, so that's good. You can even check, maybe we can zoom in or something. I don't know quite how to do that, but if we go ahead and rotate this around, we can see, okay, so this is what our region looks like right here. All right, so I went ahead and zoomed in a little bit more. So again, here's our region, and the claim is the volume of this region here would be 1, right? So if we did, it's not quite length times width times height, right? Because it's not a rectangular prism, but if we calculate out the volume of this structure right here, right? How much water would it hold, right? The claim is that it would be 1. All right, and that's all there is to it. I'll see you guys in class. We'll do a lot more of this stuff. See you then.